Lesson 52, Dynamically Allocated Multi-Dimensional Arrays. To follow along with this lesson, you will need to create a new console project and add a new file named main.cpp to it, as we did in Lesson 1. We can create multi-dimensional arrays easily when we know the desired size of the array at compile time. However, if we don't, then we need to allocate the memory for our arrays dynamically using new. We begin with a review of dynamically allocated one-dimensional arrays, since they are the basis for creating multi-dimensional arrays. In our first program, we allocate an array of 3 ints. Next, we fill it with the values 0, 1, and 2. Then we output the entries of the array with spaces between them. Finally, we deallocate the memory with delete. Let's review the syntax that we use for allocation and deallocation. For allocation, we write new, the type, which is int, and the number of integers that we are allocating in square brackets. This tells the compiler that we want to allocate memory for 3 contiguous ints. Our assignment sets the pointer IPArray to point to the allocated memory. To deallocate the memory, we use delete. However, we use the empty brackets to let the compiler know that we are deallocating an array of entries and not just one. Executing our program, we see the integers 0, 1, and 2 printed, as we would expect. Let's look at the memory layout for this allocation. In this program, IPArray is a pointer that points to the beginning of the array of allocated ints. Note that the pointer itself is not dynamically allocated, only the array of integers is. This one-dimensional case is fairly straightforward. Our second program dynamically allocates a 2-dimensional array. Much as before, we begin by allocating the memory. Next, we fill the array entries with the sum of the indices. Then we output the entries. Finally, we deallocate the array. Notice that our main pointer is a pointer to an int, and it is set to point to an array of pointers to ints. After this, we allocate the int entries of the array. We fill each entry of the array with the sum of its indices I plus j. Our memory structure looks like this. Starting with the initial pointer to a pointer, this points to the beginning of an array of 3 int pointers that, in turn, point to arrays of 2 ints. These arrays hold the entries to our 2D array. Notice that we have 4 separate arrays that are allocated, and that we have an additional level of indirection. We output the array as a series of rows. Notice that when we deallocate the array, we deallocate each row of entries, and then we deallocate the array of pointers that pointed to the rows. This is the opposite of the allocation order, which is typical when dynamically allocating memory. Executing the program, we see the entries outputted into rows as expected. Allocating a 2D array like this has great flexibility, and we can even have rows of varying length. In this program, we demonstrate this with an array of character strings. This program uses a 2D array of chars, and the structure of the program is almost exactly like the previous program, except for the row allocations and the calls to string copy to fill the entries of the array. Remember that although zoax.net is only 8 characters long, we needed to allocate 9 in order to hold the null terminator. Executing the program, we see our 3 strings outputted. This array is structured so that the strings form the rows in our 2D char array. Here we see the memory layout. We start with the base of the array, which is a double pointer. This points to an array of char pointers, and each of these entries points to a null-terminated string that is stored in an array. For our last program, we show how to allocate a 3D array. The array that we allocate is a 3D array of ints that is 3 by 2 by 4. Again, we allocate the memory to fill the array entries with the sum of the indices, output the entries, and deallocate the memory. The structure is very similar to our second program, except that we have added extra loops for the additional dimension. To start, we use a triple pointer as the base of our array. Then we allocate an array of double pointers and set the triple pointer to point to the beginning of this array. The next loop allocates an array of pointers for each of the double pointers. Finally, we allocate arrays of 4 ints for the final dimension. To deallocate the array, we do the same steps in reverse. Executing our program, we see the output of the entries of our array. 3D arrays are somewhat difficult to visualize, so we just output 3 2D arrays that are each 2 by 4. Here we have the layout of our array in memory. Everything starts from our triple pointer, which points to the beginning of our array of double pointers. Each of these double pointers points to an array of pointers, which in turn point to an array of 4 ints. These ints contain the values of our array. Notice that our 3D array is just like our 2D array with an additional layer. We can extend this method further to create arrays of any number of dimensions that we wish.